Hi, I'm Youngseok Jang from Seoul National University. The paper I'm presenting on behalf of my courses is Navigation Assistance Path Planning within a Micro Area Vehicle Team. This paper proposes a two MAV system where one MAV operates for a given mission and the other MAV supports the team navigation. From now on, I'm going to present based on this content. Firstly, introduction. Navigation and path planning are essential for autonomous MAV operations. In order to execute missions in various environments, such as GPS-denied areas, we need navigation system using onboard sensor. Also, path planning module is necessary to carry out certain missions, like target chasing, area manipulation, or map exploration. The performance of visual navigation highly depends on the characteristics of environment. In order for visual SLAM to make stable performance, feature-rich scene should be captured in image. If a camera stares at featureless area, it can lead to unstable and low-quality navigation. Navigation performance highly affects to mission success and failure. Therefore, path planner should generate paths which ensure robust navigation performance. That is, well-distributed and abundant features or high image gradients should be captured in image while moving along with generated paths. Research in path planning for stable navigation have been called perception-aware path planning. They added perception codes with their various intuitions and then formulate this problem into multi-objective optimization. Without that, the mission performance is suffered from the effort to keep navigation quality. Therefore, mission performance can be decreased. So we solve this problem by adding sub-agents serving as an intelligent sensor for navigation. Two MAV team navigation setup with monocular camera is proposed. In this team, there are two agents. The first one is a main agent, which only focuses on their mission, and the second one is a sub-agent, which supports state estimation of navigation. As you can see in figure, even though main agent moves along with mission-oriented paths and meets featureless area, sub-agent can help the navigation of main agent. Therefore, mission agent can continue a mission without navigation failure. Now I'm going to the chapter 2, problem setup. This is our framework which has centralized architecture. Both agents utilize monocular SLAM. Moreover, sub-agent has an assistance module to support the navigation of main agent. Map fusion module integrates two local maps estimated by both agents into a frontier map. Main and sub-agent planner acquire environment data from a frontier map. Main agent planner generates motion, which is highly efficient for chief mission, and sub-agent planner generates trajectory for the algo navigation as well as navigational assistance of main agent. The path of sub-agent is determined by three rewards to maintain team navigation. The first reward is perception quality, which is performance metric of navigation and is for guaranteeing stability of navigation. The second reward is quality for future steps. In the right figure, sub-agent at A position have larger future quality than at B position. Because in the long term, this A motion makes frontier map expansion, and sub-agent can generate efficient movement using much larger available map data. Last reward is action quality. It considers the dynamic feasibility of MAV and reduction of motion blur. And then we talk about the path planning for sub-agent in detail. Before moving on to details, we briefly introduce sub-agent planner. In our framework, future trajectory of the main agent is shared with sub-agent planner. Based on this future poses, we sample vertices at each time step and connect edges. In order to get optimal waypoints, we serve the graph-based optimization which is formulated by the aforementioned three rewards. Then, we make smooth trajectory using selected waypoint. We adopt spherical coordinate system to represent sub-agent pose effectively. Firstly, in this work, visual markers mounted on the main agent are used to detect main agent, and the center of the markers is chosen as the origin of virtual marker VK. Secondly, the z-axis of sub-agent camera coordinates directs the origin of virtual frame in order for sub-agent to see visual markers at all times. And then, assuming that sub-agent is always in near hover state, the pose of sub-agent can be expressed with two parameters of radius and azimuth angle in spherical coordinates. In order to sample proper vertex, we use perception and feature stack qualities. At first, we define perception quality with intuition. Localization performance of feature-based SLAM is affected by the distribution as well as the number of feature points. In the aspect of the number of features, it is important to ensure that the number of features does not fall below a certain number. So we use the covariance of features and sigmoid form waypoint to design perception quality. Next, feature stack quality QF promotes to look around the future position of the main agent. Here data theta k is the angle between the direction where main agent moves and the direction of the g-axis of sub-agent camera frame. So small delta theta k means sub-agent camera looks moving direction of main agent, and it positively affects to the expansion of a frontier map. From now on, vertex and edge generation in graph-based planner will be presented. Firstly, sub-agent planner extracts feasible domain, which guarantees stable navigation. To this end, perception qualities of vertices should be larger than certain threshold. In feasible domain, we newly define reward function to sample vertices. Rk is reward function which can be computed using perception and feature stack qualities in feasible domain. Rk assigns a relatively high weight to the feature stack qualities when the main agent's perception is high, because if main agent SLAM itself performs well, sub-agent don't need to assist the navigation of main agent. So sub-agent makes an effort on a frontier map expansion for future steps. Based on computed RK, vertices are selected with weighted sampling like this. And then we set 3 rules to determine edge connection for feasibility check. The first one is check the maximum velocity and angular velocity. And the second one is to reject the highly jerky motion. And the last one is to check path crossing to ensure main agent can be tracked during the time interval. After this feasibility check, edge weight are defined with the consideration of action cost. Here, action cost is defined as the yaw difference between two vertices in order to reduce motion blur and jerk motion. Based on the defined edge weight, graph-based optimization is solved via topological sorting. Lastly, with the optimal vertices, we generate smooth trajectory. For dynamically feasible movements, we utilize minimum jerk polynomial trajectory generation method. Okay, and the next chapter is about navigational assistance. In the map fusion module, 2 local maps estimated by both agents should be integrated into a frontier map with global scale. To this end, map fusion module should estimate the initial relative pose and scale ratio between 2 agents using visual markers. We can formulate this problem as pose graph optimization as follows, and we solve it using Levenberg-Marquardt method. The strategy of navigational assistance is as follows. In the frontier map, 2 agents estimate their ergo motion by SLAM algorithm. SLAM estimated pose of main agent is not stable as much as sub-agent pose estimation, because main agent does not consider navigational performance. In order for sub-agent to assist the navigation of main agent, we estimate navigational assistant pose, which can be acquired by minimizing reprojection error of visual markers. To determine the final estimation of main agent pose, we fuse 2 estimated poses, SLAM estimated and the navigational assistance poses. We compose the poses as follows, considering the perception quality of main agent and assisting term. In the following slides, I will share the simulation result and conclusion. We tested the proposed system with the following setting, and we evaluate the impact on the future step qualities using 2 situations. The first case is FS case without considering QF by 0 coefficient. And the second is FO case considering future step qualities. In the first environment, the main agent has a goal-reaching mission, traveling a straight path. We evaluate 2 cases of FO and FX in this simulation environment. This slide shows the frontier map and the image of sub and main agent in FO and FS cases. In the beginning, the proposed system creates an initial frontier map with the map fusion module. In the FO case, the sub-agent extends the frontier map while assisting in the main agent navigation. As you can see, the frontier map of F4 is larger than that of FX case. And the main agent fails to navigate itself, which is denoted as the red color in the frontier map. But in the proposed system, the main agent pose is robustly estimated with the support of sub-agent, as shown in the green color in the frontier map. In the second environment, the main agent traverses a U-shaped path. The beginning initial frontier map is created by Map Fusion module, and sub-agent extends the frontier map while supporting team navigation in F4 case. As you can see, the frontier map of F4 is much larger than that of FX. As you can see, when the main agent fails to navigate itself, its pose is robustly updated in the proposed team navigation setup. In conclusion, we present the two MAV systems which can effectively execute a given mission, assuring navigation quality. And we designed the navigation assistant planner of sub-agent using proposed perception and future stack quality. Lastly, we devised navigational assistance strategies with Map Fusion module. Thank you for listening to my presentation.